how do you measure something you can't even see? Think about the water you drink. How do we know if it's acidic or alkaline? We can't see acidity, but we can measure it with incredible precision. The secret lies in tiny, powerful sensors called electrodes, which act like our eyes and ears in the chemical world. Welcome, engineering students. Today, we are demystifying the fundamental tools of instrumental analysis, electrodes. Think of them as the probes that connect our measurement devices to the world of chemistry. In this video, you will learn about three key players. First, the stable anchor, the reference electrode, specifically the Saturated Calomel Electrode. Second, the active sensor, the indicator electrode, focusing on the famous glass electrode used for pH. And finally, the specialist, the ion selective electrode. By the end, you'll understand exactly how a pH meter works. Let's get started. First up, the reference electrode. Formally, a reference electrode is an electrode that has a stable and well-known electrode potential. So, what does that really mean? Imagine you're measuring the height of a building. You need a stable, unchanging starting point, right? Like the ground level. You can't measure from a moving car. A reference electrode is the ground level for chemical measurements. Its job is to provide a perfectly constant voltage, an unwavering reference point that never changes, no matter what's happening in the rest of the chemical solution. It's the anchor of our entire setup. One of the most common reference electrodes is the Saturated Calomel Electrode, or SCE. Inside, you have a pool of pure liquid mercury at the bottom. Above that is a paste made of mercury and mercurous chloride, which is also known as calomel. This is all immersed in a solution of potassium chloride, or KCl, that is saturated, meaning it's holding as much salt as it possibly can. A tiny porous plug at the bottom allows electrical contact with the test solution without letting the insides leak out. The chemical reaction happening inside is perfectly stable, giving it a constant potential of positive 0.241 volts. You will find a reference electrode as one half of almost every electrochemical measurement system. From research labs to industrial quality control, whenever you need to measure a potential, you need a stable reference to measure against. Now, if the reference electrode is our stable ground level, how do we actually measure the building? For that, we need the other half of our team, the indicator electrode. An indicator electrode is an electrode whose potential changes in response to the concentration of a particular chemical substance, or analyte, in a solution. This is our active probe. If the reference electrode is the stable ground, the indicator electrode is the measuring tape. Its voltage is designed to change. It's like a chemical thermometer, but instead of temperature, it responds to the amount of a specific ion. The most famous example is the glass electrode, which is designed to respond only to hydrogen ions, which is how we measure pH. Let's look at that glass electrode. The magic is in its tip, a very thin bulb made of a special type of glass. This glass membrane allows hydrogen ions from the solution to interact with it, creating a tiny but measurable potential difference across the membrane. The more hydrogen ions in the solution, meaning the more acidic it is, the larger this potential becomes. The electrode is essentially counting the hydrogen ions. The glass electrode is everywhere. It's the heart of every pH meter in every chemistry lab. It's used to check the acidity of soil, test the quality of milk and cheese, monitor environmental water sources, and ensure chemical reactions are proceeding correctly. It is a truly ubiquitous tool. Okay, So we have our stable reference electrode and our responsive indicator electrode. How do they work together inside a pH meter? Let's walk through it. Step 1. The setup. When you place a modern combination pH probe into a solution, you're actually dipping both the glass indicator electrode and a reference electrode like silver or silver chloride in at the same time. They're built into a single convenient body. Step 2. Potential generation. Instantly, two things happen. The reference electrode produces its constant, unchanging voltage, let's call it E reference. At the same time, the glass electrode produces a variable voltage that depends directly on the pH of the solution. We'll call this E indicator. Step 3. The measurement. The pH meter itself is just a very sensitive voltmeter. It measures the difference in potential between these two electrodes. The total cell potential, E cell, is simply E indicator minus E reference. Step 4. Conversion to pH. Here's the key. The meter knows that the indicator's potential is directly related to pH by the formula E equals K minus 0.0591 times pH. Since it knows E reference is constant and it has just measured E cell, it can solve the equation for the only unknown, pH. It does this calculation instantly and shows you the final clean pH value on the screen. Now, what if you don't want to measure hydrogen ions? What if you want to measure, say, fluoride? For that, we need a specialist. An ion selective electrode, or ISE, is a type of indicator electrode designed to be highly selective for one specific type of ion while ignoring all others. The analogy here is perfect. An ion selective electrode is like a key that fits only one specific lock. A fluoride ISE will only respond to fluoride ions. A potassium ISE will only respond to potassium ions. It's the ultimate specialist sensor. Instead of a glass membrane, it uses a unique solid-state membrane or a crystal that is designed to only allow its target ion to interact with it. Visually, an ISE looks very similar to a pH electrode. The difference is internal, in the construction of the membrane at its tip, which is tailored specifically for the ion it needs to detect. These are incredibly important in both environmental and medical fields. Municipal water treatment plants use ISEs to ensure the correct amount of fluoride is in our drinking water. In hospitals, blood gas analyzers use ISEs to measure critical electrolyte levels like sodium, potassium, and calcium in a patient's blood sample, providing life-saving information in minutes. So, let's do a quick recap. The reference electrode, like the calomel electrode, is our stable, unchanging anchor point. The indicator electrode, like the glass electrode, is our active sensor whose voltage changes in response to an analyte like hydrogen ions. And the ion selective electrode is a highly specialized indicator that acts like a unique key for a single specific ion. Together, they form the basis of how we precisely measure the invisible chemical world around us. If this video helped you understand the fundamentals of electrodes, please hit the like button and subscribe for more engineering content. Have a question? Drop it in the comments below. Thanks for watching.